Hello, class. This is Mr. Hart, and in this podcast, I want to start the Earth's atmosphere chapter. And to start out, we're just going to look at some of the properties of the Earth's atmosphere. Okay, and that consists of all the air around us and around the Earth. And first of all, we want to look at what is the atmosphere made of, and the atmosphere has an interesting composition. Okay, it's about 78% nitrogen and 21% oxygen, and then 1% other stuff, basically argon and carbon dioxide and hydrogen and helium and things like that. Okay. But this really surprises people sometimes. It's 78% nitrogen because we breathe in oxygen as humans. And so a lot of people think that oxygen would be the main part of the air, but it's actually not. It's only a small fraction, about a fourth of the air. But we'll get more into why nitrogen is so prevalent in the Earth's atmosphere a little bit later, but just realize for right now that nitrogen makes up most of the air, then oxygen makes up a good chunk, and then there's everything else that makes up a very small amount. Okay. Then we moved on to different properties of gases, the mass of gas, the volume of gas, density. Okay, and specifically we want to talk about air pressure and density. So imagine you had a water bottle and you crushed it, okay, when you were near the sea, okay, at sea level. Then, if you brought it up to the mountains, what would happen? Well, as you raised in altitude, the pressure around the bottle went down, okay, and so the bottle is actually going to expand because you have a higher pressure inside the bottle. So I like to represent it with an H, okay, for high pressure, and L's for low pressure. Okay, so imagine if I took the bottle up to the atmosphere, or up higher into the atmosphere, up on like a mountain or something, the high pressure in the bottle is going to push out towards the low pressures, which is going to cause the bottle to expand. Okay, this is the same reason like a bag of chips. Okay, have you ever seen a bag of chips at Walmart or something and it's all filled with air? That's not because they intentionally fill it with that much air when they package it, but the reason is they package it at sea level. Lay's factories in Plano, Texas, for example, that's near sea level. And then when they bring it up here into Utah near the mountains, the bag's naturally going to expand because of this high pressure in the bag and low pressures on the outside. Okay, and so I always draw it like this. Okay, or think of it like this: high pressure will always flow or push towards low pressure. Okay, no matter what the situation is. All right, and so again, the pressures do vary as you go from sea level up to an altitude. Okay. At sea level, the air is very dense, and the higher and higher you go up in the atmosphere, the particles become less and less. They become more sparse, and so the pressure goes down. So you'd have very high pressure down here, very low pressure up here. So down at sea level, you'd expect a higher pressure. Up in the mountains around here, you would expect a lower pressure. Okay, which is why that bag of chips or that water bottle expands. Okay, but let's keep talking about high pressure pushing on low pressure. I do an experiment in class where I take this pop can and I put some water in and I boil the water. Well, that boiling water gets some high pressure in the can, which pushes the air out. But then I put it into this cool water in this container over here, and that instantly lowers the pressure. So then a lower pressure on the outside, lower pressure on the inside and a higher pressure on the outside pushes in on the can and collapses it. So if you want to see that, you can go to this video right here. Okay. There's also this video we watched. Okay, same idea, but they do it with this egg in this bottle. They make a low pressure inside the bottle, and the high pressure can actually push the egg through the bottle. Okay, so you create a low pressure here, create a high pressure on the outside, and so that will actually push the egg into the bottle. Okay, so that's also very cool, and you can find at this address. Okay, and so again, we watch a lot of videos in class, do a lot of experiments because it's just really cool to see how much pressure you can get, and you can really see how strong it is, because it can even collapse a steel can. In this video, they cool a steel can with high air or with steam in it that cools down, creating a low pressure, and can collapse this entire steel can. Okay, so it's pretty extraordinary. This one does it in slow-mo. So again, there's a lot of cool videos we watch of just this differences in air pressures, which causes these really cool effects. Okay, but again, it's just the same basic principle: high pressure pushing on low pressure. Okay, some applications of this are, for example, if you are cleaning a rail car, they use this high-powered steam gun with these chemicals and all this stuff to clean out these freight cars and these different train cars. And when they do that, you do not want to close the steel or the hatch on these steel compartments, because if that steam from all the cleaner cools down, that creates a low pressure inside this compartment. And so if you close that hatch all the way, then you have a low pressure inside the rail car and a high pressure on the outside, which can collapse the freight car. So this is not an explosion. This is not some type of force someone put on this. This is just the rail car imploding from air pressure. Okay, so this is what you do not do. Okay, you do not close that hatch after you clean a rail car, or that can happen. Okay, so again, just lots of examples of air pressure and its effects. Okay, we also looked at this simulation. Okay, it kind of gives us a good idea. It's at this web address. It gives us kind of a simple picture of how the pressure looks like with the molecules. Okay, if you put the molecules closer together, then they're moving faster, which creates a higher pressure. If you bring them far apart or farther apart, then they spread out, they slow down. So it's kind of just a good visualization of this air pressure. Okay. All right, and then we talked about atmospheric pressure, what it is actually measured as. Okay, and so 1 atmosphere, this is the unit they use, or basically the pressure of the atmosphere, or the atmospheric pressure. So 1 atmosphere equals 14.7 psi, or pounds per square inch. Okay, and so that's pretty strong if you think about it. If you make a little circle with your hand, okay, and you think about it, that might be about a square inch. That means for every little square inch that you make, that's 14.7 pounds that the air puts on that little circle. Okay, so if you have all that pressure on you, okay, 14.7 pounds for every square inch of your body, why do we not collapse from this effect? It's just because of our body is able to put as much force out that the air pushes in. Okay, so again, you can look more into that if you want, but it's really quite a strong force. That's why it can collapse that steel can. Okay, those steel drums. Okay, well, let's talk about how they actually measured this atmospheric pressure. Okay, and how they actually do it is what we call a barometer. Okay, so a barometer has some mercury in this little container right here, and mercury is actually this metal liquid. It's kind of the only metal that's liquid at room temperature, and it's a very useful substance, just because it's very thick. It's again a metal, so it's a good conductor. So they used it a lot historically, but we don't use it as much now because we realize it has a lot of dangerous properties. It's very poisonous and can cause problems to the nervous system and other things like that. But back in the day, what they use is they put this mercury in this a little tub, you could say, and they put a vacuum up here, which is basically meaning no air, right? So very, very low pressure. Okay, so you have very low pressure here, you have very high pressure, or relatively high pressure, on the outside. Okay, so what happened is the high pressure on the outside is going to push in on the mercury and try to go up to that low pressure. Okay, so as it does that, it pushes the mercury up through this tube. Okay, and so based on how strong this pressure is on the outside, and based on how high this mercury goes, we can tell what the atmospheric pressure is for that day or for that altitude or whatever it is, because this will go up and down. Okay, and as it goes up and down, we can say, oh, this point would be 14 psi, and this point would be 15 psi, and this point would be 13 psi and 12 psi or whatever it is. Okay, so as that mercury goes up and down the tube, we can determine what the atmospheric pressure is. Okay, so again, the same idea: high pressure flowing to low pressure. Okay, and so this is how they historically found atmospheric pressure. Okay, and today we use a similar type of tool, but again, we don't use mercury. Okay, or in most cases, don't use mercury because it's very dangerous. Okay, and so basically, the main thing again I want you to remember for this part of the chapter that will really is really the simple idea for the whole this whole part of the first part of the chapter is that high pressure flows to low pressure. Okay, hopefully that makes sense, and let me know if you have any questions. And I definitely recommend going back through those YouTube videos and watching them because they're very cool. But that is it for this podcast, and thank you for watching.